Hello and welcome to our lesson on Newton's third law. So today's goal, I want you to be able to explain Newton's third law and apply it to real-world situations. So, what does Newton's third law state? Well, Newton's third law states that for every action, there is an equal and opposite reaction. So let's take the example of a person striking a wall. So there's my wall, there's the person, good old stick man, and there's his fist, boom. So if we do a free body diagram here, and we look at the fist itself, so here's my fist, there's the applied force. Now the wall isn't moving, so if it's not moving, it is applying an opposite reaction force, which I'll call FR for now. So there we are. So if the wall doesn't move, forces have to be balanced. So as hard as you hit the wall, you are going to feel that back on your knuckles or your fist. Okay, so every time you apply a force, there is an equal and opposite reactionary force. So a card has a chamber inside it, and I'm going to sketch that up. So here's the sketch. So card has a chamber inside it where there's a spring, so that's my green twirly or spinny line. And then it's a ball, and I painted my ball blue. The cart is 1.2 kilograms. So mass of the cart, 1.2 kilograms. So I'm going to start my list again. The ball, so mass of ball is 0.07 kilograms. And the spring exerts, so force due to spring, 2 newtons of force to the right, and we're talking about acting on the ball here. So answer the following. A, identify 3 action-reaction pairs of forces when the spring is released. So, what is an action-reaction force? So I'll just sum this up with a T-chart. Reaction. So, if the action is the spring on ball, well, if the spring acts 2 newtons on the ball, conversely, the ball will act on the spring. So as much as the spring pushes the ball is also pushing the spring. So if we follow the spring, on the other end then, the spring on cart, well, the reason the ball will shoot away is because the cart is acting on the spring. All right. Similarly, and you can continue this on back as far as we want to go here. Cart on, you can pick wheels or ground. Cart on ground. The ground is acting on cart. So you can see it goes, there's these action and reaction forces. So for every action, there's an equal and opposite reaction that we need to be concerned with. So that's A. B part. Draw a free body diagram of the ball and then calculate its acceleration while the spring is pushing on it. So, if we look at the ball, here's my free body diagram. Okay, we're going to assume that the force due to gravity, Fg, and the normal force are equal because it's in the chamber. The unbalanced force is 2 newtons, so it's pushing it to the right. So let's find the acceleration here. Well, we know Fu ma, that's the acceleration. So we've got 2 equals 0.07 A. So A will equal 28.6 meters per second squared right. Okay, and there we go. Now let's just talk about this for 1 second, and I want to ask you, what happens if the wheels are free to roll? So let's look at the cart for 1 second, for argument's sake. Free body diagram on the cart. If the ball pushes off with 2 newtons, similar to if you're on a raft, if you jump off the raft goes flying behind you. Similarly, the cart is being pushed on by 2 newtons. The ball is acting on the cart. It's pushing on the cart. So if we don't worry about, we have our force due to gravity, we have our force due to normal. The cart then is also going to accelerate in the opposite direction. So I know it's not part of the question, but here's your action-reaction force. So the ball is going to go 28.6 meters per second squared to the right. The cart is going to go 1.2. If I calculate the acceleration there, so our 2 divided by 1.2, it's going to go 1.7 meters per second squared to the left. Okay, so action-reaction, if you think back to, for some maybe the history buffs here, the large cannons that they used in World War II, they had to put sort of, if this was the cannon wheel, they put these blocks in because the cannon, when it fired, would rock back. Well, why is it rocking back? Well, the explosive force in there that fired the shell would push the shell forward, but it would also push back on the cannon with equal force. Same thing if you think of people that fire a rifle or a gun. Why does it kick in your hands? Well, when you shoot the bullet, the hammer triggers the gunpowder and fires the bullet. So it acts, the gunpowder acts on the bullet, pushing it forward. Well, the bullet pushes back on the gun, and that's how you get your recoil. That's why we have recoil. So Newton's third law is why we have recoil when we fire a weapon like that. Okay? So that finishes off that example. Some real life applications for you. Okay? Tires. How do cars move? Actually, how do we walk? When we have tires, we have the axle that's transferred the motor force all the way down to the axle of the wheels. Okay, which way, if you're going to the right here, if your direction of travel is this direction, then your wheel is rotating forward or clockwise, and it is applying a force in this direction. Okay? Well, the only reason that wheel that we're allowed to move forward is a reaction force reaction, because if there was no force opposing it, then what would happen is that you would just sit there spinning your tires. You wouldn't go anywhere. So that reaction force is very, very important, and our reaction force here is generated by the friction at that point. Similarly, jet engines. How do jet engines work? Well, we have what we call fuel, and I've simplified this down. So the fuel will go into the injection chamber here. We have oxygen in, or air, we'll call it at this point. So air. In here we get a big explosion, sparks, boom. So we have combustion. What does combustion create? It creates heat, which expands gases. So if the explosion expands the gas, we have a wider opening down here. So this is a wider opening taking in air. Now we have a smaller opening at this end. So now we have this expanded gas trying to get out, and it's going to come out at a higher velocity. Think of if you have a garden hose and you're spraying your friend. If you cover part of the hole, it will come out much faster. If I pump more water into the hose, it comes out faster. So what's happening is that explosive force is coming out of the back of the engine, so the air is rushing out very, very fast. Why does it work then? Well, because behind the engine are air particles. So we have air particles. And what happens then is that they push back. So the free body diagram, here's the force due to the engine, the air coming out, and here's your reaction force. It's the air particles pushing on the air that's coming out. So it's that reaction back here that allows a jet engine to move. All right, it's that air rushing out, pushing against air. Okay, so that would mean in space, jet engines wouldn't work. Why would they not work? Would not work. Oops. And why is that? Well, no atmosphere for expanding gas to push against. To push against. Okay. So what they're doing in space, when the shuttle, you see it moving, there's these little puffs. All they're doing is they're actually just expelling air, and it's that Newton's third law that rotates or pushes it because it's the air is being expanded out, so it's the reaction of the air being ejected versus the surface of the shuttle. So the action-reaction force, if this is the little air jet where you see that poof of air come out in the movies, this is where that interaction's happening at the surface. This out here is just where the air is traveling. So it's that interaction force at the surface, the air pushing against the bottom of the canister. Okay, so kind of neat. So Newton's third law allows us to be able to move, to drive without friction. We wouldn't be doing a whole lot. So homework is there for you at the bottom. Looking at a couple of questions on 148. And then I have a handout as well. You'll find it with the previous journal package for you to work on. If you have any questions, let me know and we can go through and kind of clarify Newton's third law as we go. Good luck.